Welcome back, students. So, in the last lecture, we discussed about the observations on photoelectric effect and what were the main thing like importance of threshold frequency. How did photocurrent change with intensity? Then we discussed about how the kinetic energy depends on the or stopping potential basically depends on the kinetic energy. So all those things we discussed in the last lecture, that is lecture 3. So just go through that lecture 3 once again, right? So in this lecture we are going to see whatever were the observations on photoelectric emission, how those observations were explained by Einstein. And I'll just tell you a very important point that the Nobel Prize was awarded to Einstein for his explanation on photoelectric emission. So, if you see before this, so earlier, as the topic goes, the topic heading is dual nature of radiation, right? So, what are the two things or what are the two natures of radiation? That is what we are going to discuss in this particular topic. So, as per the earlier theories of light, two very important persons contributed to the theories of light. One was Christian Huygens, and second was James Clerk Maxwell. These were the two persons who contributed to the explanation of what is known as the wave theory of light. And using wave theory of light, they could explain many phenomena which we'll be studying later on, like interference, diffraction. These two phenomenons of light, they were explained in by Huygens as well as Maxwell. So Huygens theory was that light is made up of particles which are vibrating, and same thing was Maxwell's theory that light is made up of oscillations of electric and magnetic field. But then if light is considered to be a wave, so a very important discussion on this particular thing is that if we consider light as a wave, then now this point is very important, that if you consider light as a wave, then if I increase the amplitude of the wave, right? If I increase the amplitude of the wave, then there must and should be increase in the kinetic energy. Indirectly the stopping potential should increase. This is a very important argument here, that why wave theory does not apply in photoelectric emission, and why it is a drawback of the wave theory. So as if you apply wave theory, then what basically should happen is, as I increase the intensity, can you see in this graph, I1 is increased to I2, I2 is increased to I3. So if I increase the intensity of light, then as per wave theory, the kinetic energy should increase, and hence the stopping potential, that should basically increase. But practically if you observe that if I increase the intensity of light, there is no change in the stopping potential or this retarding potential which we see over here. So this is the first important point which shows us that the wave theory does not practically be applicable on light for this particular effect, that is photoelectric effect. Another important discussion, if I see over here, that if I increase the frequency of light, as you can see, mu1, mu2, mu3, as the frequency of light is increased, there must and should be an increase in photocurrent as per the wave theory of light. So it's a very important understanding here. It requires a little bit of imagination, a little bit of understanding about wave, that if you consider wave, then it has an amplitude. Then as I start increasing the frequency of light from mu1 to mu2, mu2, mu3, there must and should be an increase in the photocurrent. But practically if you see, this photocurrent doesn't increase with increase in frequency. On the other contrary, the kinetic energy increases, which is totally which was not at all predicted as per wave theory. So these two observations, they do not support the wave theory of light. What is the first observation which does not support the wave theory of light? The first observation is that if I increase the intensity as per wave theory, kinetic energy should increase, but kinetic energy is not at all increasing of the photoelectrons. And second very important observation is if I increase the frequency, there should be again increase in photocurrent as per wave theory, but practically the photocurrent, you can see this flat line over here, that mu1 is increasing, mu2 is greater than mu1, mu3 is greater than mu2. That means frequency is increasing, but you can see that the current remains flat. So these things couldn't be explained by Leonard Halbachs. They couldn't be, of course, Hertz just was the discoverer of photoelectric effect. So Einstein, very in detail, he explained the photoelectric emission. I'll just show. This was the what do you call it as the research paper which was presented by Einstein. During that time, he was just 26 years of age. It was the year 1905. And for this particular explanation, Einstein was awarded the Nobel Prize. Now, what was different about Einstein as compared to the earlier theories? That first of all, Einstein, very important thing what he said was light is not a continuous stream of a wave. Light consists of discrete particles. Discrete means separate particles. So it is a stream. It is a stream of what you call it as small particles known as photons, and these photons are not in a continuous way. Okay, these are discrete. The meaning of this word discrete is separate. So photons, he said that light consists of a stream of photons, and every photon has an energy which we already discussed, given by E is equal to h mu, where the value of h is nothing but the Planck's constant. It is 6.626 into 10 raised to minus 34 joule second. As we had already discussed earlier, that of course energy of each photon is given by E is equal to h mu. So he used Maxwell's theory, and in Maxwell's theory, he showed that Maxwell's theory can be proved if you assume that light is distributed discontinuously in space, in the sense that light has what you call it as it is a stream of photons, and these photons are like separate from each other. Even though light continues, it looks like a continuous beam, but within the beam these photons are basically separate. So this is a very important thing which Einstein contributed in understanding of light, that light consists of discrete packets of energy, and these each discrete packet of energy, they are basically known as photons. Okay, then he said that the electrons are bounded by the ions because of the that is interatomic forces. So in order to first separate the electrons from the ions, the free electrons from the ions, a minimum energy should be provided to the metal, and that minimum energy which we already discussed, that is known as work function, and this threshold frequency is equal to phi naught is given by which one, h. So Einstein said a very important statement. Please, if you can just see this particular line over here, that when a photon goes and hits the electron, it gives its complete energy. The complete energy E is equal to h mu. So just see, when a photon goes and hits the electron, it gives the complete energy to the electron, and when this electron, it absorbs this complete energy. Yeah, if you see this diagram, the energy which is given to the electron, it is utilized in two different ways. First is to overcome the binding energy, and that to overcome the binding energy, we require the important thing which is known as the work function, right? So first of all, what is the thing, that the photon, So this very important statement that the moment the quanta or the photon of light it goes and hits the electron, it gives all its energy to the electron, right? And once it gives all its energy to the electron, what does that electron do? What does it do with the energy? First of all, some part of the energy is utilized to overcome the binding energy. Electrons are attached to the ions, so some part of the energy is used to overcome the binding energy, and the remaining part of the energy that is provided to for what you call it as the kinetic energy of the electron. So if I put it in equation form, it is something that uh, energy given by a photon, that is equal to work function plus kinetic energy. So from where did this energy come? This energy came from the photon of the incident radiation when it falls on the metal surface. Where it is utilized? It is utilized in two important things. Which are the two things? One is it is utilized for doing the work, and second thing is for the kinetic energy. So work function for a given metal remains the same. As you increase the frequency, kinetic energy basically will increase. Okay, so this equation, okay, that we'll just put over a minus sign over it. Okay, so this equation, kinetic energy, and remember here, the kinetic energy which we are dealing here is kinetic energy is the maximum kinetic energy of the emitted photons. So if you see this formula here, kinetic energy is given by h mu minus phi naught. Again here, phi naught it basically represents the work function, h mu is the energy of the incident radiation, and k max is the kinetic energy. You know, kinetic energy is half mv square. So kinetic energy is equal to h mu minus phi naught. This is the famous Einstein's photoelectric equation. So if I come back to this particular diagram over here, that whenever an electron gets the or a photon comes and hits the electron gains the energy. What does it do with the energy? The energy is utilized in two ways. First is to overcome the binding energy, so electron gets knocked out from the ion, and the remaining energy is its kinetic, which gives its velocity. Okay, so when it basically means that more the frequency of light, okay, then obviously what will happen? If the frequency increases, there will be more and more kinetic energy. And second important thing, whenever intensity is increased, see this important point, whenever the intensity increases, it means that more and more photons are falling. Intensity does not, when I increase the intensity, frequency remains same. Like for example, instead of using one green color light bulb, I am using 10 green color light bulbs. When I use 10 green color light bulbs instead of one green color light bulb, what I have done, I have increased the intensity. So when I increase the intensity, it basically means that I am making more and more electrons fall on the surface. And then we have, again we'll go back to this particular equation, that when I increase the frequency, kinetic energy will increase. But why does photocurrent increase? If you see this particular graph over here, why does photocurrent increase with increase in intensity? Einstein explained that when I increase the intensity, more photons are falling on the metal surface, and if more photons are falling, more electrons are liberated. Okay, so this important equation was used to describe the phenomenon. Second very important thing, that why should there be a threshold frequency? That was explained by Einstein. What he said, that kinetic energy of the electrons can never be negative. You can never have a negative kinetic energy. Kinetic energy is always positive. If an electron is coming out, means it has velocity, it has kinetic energy. So kinetic energy must be positive. It indirectly means from this particular equation, it can only be possible when h mu is greater than h mu naught. What is this h mu naught here? H mu naught is the work function. Indirectly, the photoelectric emission will only take place. The electron will come out only and only if mu is greater than mu naught. So this is the second very important thing we'll have to explain in the Einstein's explanation of photoelectric effect. That as the frequency is increased, you will see that uh, unless and until the frequency is greater than threshold frequency, you are not going to have a photoelectric emission. Okay. Then regarding this, why this stopping potential is proportional to frequency, and why do you have this slope which is same whether it is for metal A and metal B. Please go through your understanding of equations of a straight line. If two lines are parallel, it basically means their slope m is same. You can have two lines, 10 n number of lines which are parallel to each other, but if the lines are parallel, surely all the lines have the same slope. So this graph, it shows two important things, that stopping potential is proportional to the frequency, and then the slope is same. So just come to this particular equation. From the equation, kinetic energy is equal to h mu. Okay. So here of course minus h mu minus phi naught. Substituting kinetic energy is E V naught. We'll get E V naught is equal to h mu minus phi naught. If I take this E down here, I'll get V naught is equal to H by E mu plus phi naught divided, that is minus phi naught divided by E. So here, uh, stopping potential V naught is equal to H by E mu minus mu phi naught by E. So we should understand that for a given metal, phi naught will always remain constant for a given metallic surface. Say if I am using sodium, always phi naught here, which is the work function, that will always remain constant. E remains constant, so phi naught by E can be compared to C in an equation of a straight line. Your V naught is the y axis. Can you see this? V naught is which axis here? Y axis. Then mu is the x axis. Mu is here which axis? X axis. So we can say that this equation, y corresponds to V naught, m corresponds to h by e, and phi naught by e corresponds to c. This equation almost resembles the equation of a, almost why it is the equation of a straight line, where you are plotting a straight line between which one, stopping potential and mu. So Einstein was able to explain these three important things, that why you have a graph where all the slopes are same. As you can see here, the slope here, which is a slope, the slope here is h by e. H is a constant, e is a constant. Okay, normally m is the slope. Comparing the two equations, which is m here, h divided by e. So as this is the slope over here, we see that this equation V naught is equal to h by e mu minus phi naught by e resembles the equation of a straight line. Hence Einstein could explain why you get a graph of this nature. If I come back to this particular two graphs, why do you get this particular graph of, why does photocurrent increases? What was Einstein's explanation for this graph? Einstein said that as the intensity increases, more and more photons fall. Say if one photon falls, one electron comes out. If 10 photons fall, 10 electrons will come out. If 10 electrons come out, more electrons come out, the photocurrent here, this photocurrent will go on increasing. And second important thing is say that as I increase frequency, coming back to this particular equation, as I increase this particular frequency, basically the kinetic energy will increase. Okay, and if kinetic energy increases, you see from this particular graph here, that if kinetic energy increases, you require more and more stopping potential to stop the electrons. So the stopping potential also, or the retarding potential, goes on increasing. So this is how Einstein basically explained the photoelectric emission. So in Einstein's explanation, so three important things which basically Einstein said was, first thing said that he said that uh, basically all the electrons, uh, or this photoelectric emission which we have, the light, the first important thing is that light consists of particles known as which one? Quanta. Second important thing what Einstein said was, whenever a photon or this quanta of energy comes and hits the electron, the complete uh, energy is absorbed. And then he started explaining that more the intensity, okay, as you can see this two graphs over here, the more the intensity, more will be the stopping potential. See here, more the intense frequency, more is going to be the stopping potential, because more and more kinetic energy, and then more the intensity of light, more will be the photoelectrons. So these four important things, if you are able to explain, so normally it's a 5 mark question. Explain Einstein's explanation, that is explanation of photoelectric emission. So that light consists of a photon. Then he gave that equation, you will have to mention this particular equation over here. This is a equation which explains it, that more the frequency of the incident light, mu, more will be the kinetic energy, and based on this you can explain the other two graphs. Okay, so with this I conclude this particular lecture. So just once again, you can, if this just if you are unable to understand first time, repeat the lecture once again. Slowly you'll understand the concept, that what was basically Einstein's explanation for photoelectric emission. Thank you.